Centrifugal pumps, fans, and compressors, vibration fundamentals and diagnostics, understanding vibration analysis for rotating machinery health. Basic operation of centrifugal pumps, fans, and compressors. Centrifugal pumps, fans, and compressors are turbo machines that transfer energy from a rotating shaft to a fluid by means of an impeller or rotor. Although their purposes differ, pumps primarily move liquids, fans move large volumes of gas at low pressure, and compressors increase gas pressure. Their fundamental operating principles are similar. Fluid enters near the center of the impeller, the eye, where it is accelerated radially outward by centrifugal force as the impeller rotates. This increase in velocity is then partially converted into pressure as the fluid passes through stationary components such as volutes, diffusers, or casings. From a vibration perspective, these machines are influenced not only by mechanical forces such as unbalance, misalignment, and bearing defects, but also by hydraulic and aerodynamic forces that are unique to fluid handling equipment. Pressure pulsations, flow disturbances, and interaction between rotating and stationary components create characteristic vibration signatures. Understanding the basic operation is essential because vibration patterns are strongly dependent on operating conditions such as flow rate, suction pressure, discharge pressure, and gas or liquid properties. Small changes in these parameters can significantly alter vibration amplitudes and frequency content. Therefore, vibration analysis of centrifugal machines must always be interpreted in the context of how the machine is operating at the time of measurement. This foundational understanding sets the stage for identifying specific vibration sources such as blade pass frequency, cavitation, turbulence, and looseness. Mechanical and flow-induced vibration sources. Vibration in centrifugal pumps, fans, and compressors originates from a combination of mechanical and flow-induced sources. Mechanical sources include rotor unbalance, shaft misalignment, mechanical looseness, bearing defects, and structural resonance. These faults are common to most rotating machinery and typically manifest at shaft rotational frequency, 1 order, and its harmonics. In contrast, flow-induced vibration is more specific to turbomachinery and arises from the interaction between the rotating impeller blades, vanes, or lobes and the stationary components such as volutes, diffusers, and casings. As each blade passes a stationary obstruction, it generates a pressure pulse, producing a periodic forcing function known as blade, vane, or lobe pass frequency. Additional flow-related issues such as cavitation, turbulence, recirculation, and starvation introduce broadband or modulated vibration patterns that differ significantly from purely mechanical faults. These flow-induced phenomena are highly sensitive to operating conditions and often change rapidly with process variations. A key challenge for vibration analysts is distinguishing between mechanical and hydraulic or aerodynamic causes, as they may coexist and interact. Correct diagnosis requires correlating vibration data with process data and understanding the physical mechanisms that generate each vibration signature. Calculation of blade or vane or lobe pass frequency, identifying blade pass frequency in a vibration spectrum. Blade pass frequency, BPF, also referred to as vane pass frequency, VPF, or lobe pass frequency in positive displacement machines, is a fundamental concept in the vibration analysis of centrifugal equipment. It represents the frequency at which rotating blades, vanes, or lobes pass a fixed point on the machine casing or diffuser. The calculation is straightforward. BPF equals the number of blades, vanes, or lobes multiplied by the shaft rotational speed. When speed is expressed in revolutions per second, Hertz, the resulting BPF is also in Hertz. For example, a centrifugal pump with 6 impeller vanes operating at 1,800 revolutions per minute, 30 Hz, will have a vane pass frequency of 6 times 30 is equal to 180 Hz. In spectrum plots displayed in orders, the blade pass frequency will appear at an order equal to the number of blades. This calculation allows analysts to predict where BPF should appear in the vibration spectrum before reviewing the data. Accurate blade count and speed information are therefore essential. Understanding how to calculate BPF is critical because it provides a direct link between machine geometry, operating speed, and observed vibration peaks, enabling reliable fault identification and trending. In a vibration spectrum, blade, vane, or lobe pass frequency typically appears as a discrete and often prominent peak at a frequency higher than the shaft rotational speed. In centrifugal pumps, it is common for the vane pass frequency to be one of the dominant spectral components, even under normal operating conditions. The analyst identifies this frequency by first determining the running speed, one order, and then locating the peak at the calculated multiple corresponding to the number of blades or vanes. Harmonics of blade pass frequency may also be present, particularly if there are nonlinearities in the system such as wear, looseness, or flow disturbances. In order spectra, blade pass appears as an integer order equal to the blade count, making identification even clearer. Correct identification is important because changes in amplitude, the appearance of harmonics, or modulation sidebands around BPF often indicate developing problems such as impeller damage, diffuser issues, or abnormal flow conditions. Why blade pass frequency amplitude increase, harmonics, and sidebands? An increase in amplitude at the blade, vane, or lobe pass frequency is usually a strong indicator of an underlying problem within the machine. Physically, blade pass vibration is driven by pressure pulsations created as each blade interacts with non-uniform flow fields or stationary components. When flow becomes uneven due to wear, erosion, cavitation, fouling, or operating far from the design point, the magnitude of these pressure pulsations increases, resulting in higher vibration amplitude at BPF. Mechanical issues such as rotor or casing eccentricity, misaligned or loose diffuser vanes, and impeller damage can further intensify these forces. Harmonics of blade pass frequency indicate nonlinear behavior, often associated with severe flow disturbances or structural interactions. Sidebands around blade pass frequency, typically spaced at running speed, one order, indicate amplitude or frequency modulation. This modulation is commonly caused by looseness, eccentricity, or cyclic variations in blade loading. Understanding these mechanisms allows the analyst not only to detect a problem, but also to infer its root cause based on the detailed spectral pattern. Cavitation and its vibration signature, turbulence and flow restriction effects. Cavitation is a flow-related phenomenon that occurs when local pressure in a liquid drops below its vapor pressure, causing vapor bubbles to form and subsequently collapse violently as pressure recovers. In centrifugal pumps, cavitation is often associated with insufficient suction pressure, excessive flow demand, or pump starvation. From a vibration standpoint, cavitation produces a distinctive signature characterized by high frequency, broadband vibration often described as a raised noise floor or a hump in the spectrum, typically between 15 orders and 35 orders running speed. This broadband energy results from the random, high-energy impacts generated by collapsing vapor bubbles. In the time waveform, cavitation often appears as random bursts of high-frequency energy and is sometimes audibly described as sounding like gravel passing through the pump. While blade pass frequency may still be present, it is often superimposed on this elevated noise floor. Recognizing cavitation early is critical, as prolonged operation under cavitating conditions can cause severe impeller erosion and premature failure. Example spectrum and waveform illustrating cavitation with a raised noise floor and random high-frequency energy bursts. Turbulence in pumps, fans, and compressors is induced when normal flow patterns are disrupted by restrictions, obstructions, or improper operating conditions. Common causes include blocked or dirty filters, abrupt changes in duct or pipe diameter, sharp bends, partially closed valves, and operation well away from the best efficiency point. In vibration spectra, turbulence typically appears as low-frequency, broadband energy rather than discrete peaks. This energy is often observed below running speed, commonly between 0.5 and 0.8 orders. Unlike cavitation, turbulence does not usually generate high-frequency noise but instead reflects large-scale, chaotic flow structures interacting with the machine. Because turbulence-related vibration can resemble unbalance or looseness at first glance, it is important to consider process conditions and system geometry when diagnosing this fault. Addressing turbulence often involves correcting the flow path rather than repairing the machine itself, representative spectrum showing low-frequency broadband energy associated with turbulent flow. Vibration characteristics of a loose impeller. A loose impeller on the shaft is a serious mechanical condition that can significantly alter vibration behavior in centrifugal machines. When the impeller is not rigidly fixed, its position relative to the shaft and casing can vary slightly during rotation. This variation modulates the forces generated at blade pass frequency, resulting in a characteristic spectral pattern. The most common indicator is the presence of sidebands around the blade or vane pass frequency, spaced at the shaft rotational frequency, 1 order. These sidebands arise from amplitude modulation caused by the changing blade-to-casing clearance or fluctuating hydraulic loading. In some cases, harmonics of blade pass frequency may also increase. In the time waveform, looseness may appear as periodic impacts or distortion. Early detection is critical because a loose impeller can lead to severe mechanical damage, including shaft wear, keyway damage, or catastrophic failure. Understanding this signature allows maintenance teams to intervene before secondary damage occurs. Illustration showing blade pass frequency with harmonics and sidebands indicative of impeller looseness.